Good morning, good afternoon, good evening to all of you. Thanks for attending this 8th Euredos webinar. This webinar is part of a monthly series organized by the European Association of Dosimetry. And today we'd like to focus on the Euredos self-sustainable intercomparison exercises for personal dosimeters. This action is clearly in line with in the scope of working group 2, which aims at fostering harmonization in individual monitoring. Such intercomparison exercises have started more than 12 years ago now, and with a success that has never faded since yet. Today, we'd like to look back on all these exercises to see what are the lessons learned for both the participants' point of view and the organization groups. So first, let me introduce my colleagues. And the agenda of the webinar. Tom Grimbergen from Mirion will give you the main outlines of the intercomparison series organized by Working Group 2. Then Hannes Stedman from Salesforce Laboratories and Ana Maria Romero from Schemat will give you the lesson learned from individual results for photon and beta intercomparisons. And finally, Elena Fantuzzi from Enea will underline the specificities for neutron intercomparison. And myself from ISN, chair of Working Group 2, just acting as the moderator today. All of us are members and or coordinator of intercomparison of Working Group 2. Before going any more further, let me remind you the Euredos rules. So do not hesitate to write any question you have online on the Q&A session on the right of your screen. Whenever you want during the webinar, there will be a specific session at the end of the webinar to answer to these questions. And if needed, if some more question happens after the webinar, do not hesitate to write to my email address that is on screen. This webinar is recorded and the recording will be available on the Euredos webpage and the slides also. So before leaving the floor to Tom, we wanted to know and to share this information with you who is attending this webinar. So we'd like to launch a first poll. So please, could you answer to this first question? What type of organization do you work for? If it's individual monitoring service and that has already participated for one or more in Euredos intercomparisons, individual monitoring service never participated to intercomparison, calibration services, commercial company, public institution, university, research center, or other. So now I will give the floor to Tom Grimbergen, who is the General Manager, Mirion Dosimetry Services in the Netherlands and coordinator of the steering committee for the photon and beta intercomparison. So, Tom.
Yes, thank you, Marianne. So what I will do is start with a few lessons learned for the organization of the intercomparisons. The lessons learned from the results will follow. I will try not to take too much time on this part because everybody is, of course, much more interested in the results. So just to start with the organization, who is the organization, Euredos? For most intercomparisons, we worked with a so-called organization group, and for the all intercomparisons, excluding the neutron dosimetry intercomparisons, the organization group, the core organization group, remained the same throughout the last decade, and even a bit more. So the names are here on the listed. Apart from this core group, we've worked with many additional collaborators, for example, the online platform administrator. Hey, I'm losing my presentation now. I don't know what happens. Yeah, it's back. Christian Gebner, and also additional coordinators listed here. Of course, also the work was not possible without the support from other Working Group 2 members and the Working Group 2 chairpersons, and the support from Eurodus office, treasurer, chairperson, council, etc. As a short overview of the program of intercomparisons we are talking about, you see in the graph a list starting in 2008 with an intercomparison for photons. And the whole aim of the program was to have to provide regular scheduled intercomparisons for individual monitoring services. And the way we did it was to organize it in a self-sustained way, which means we don't have any, we are not reliant on any external financing. It's all paid by the participants themselves. And these intercomparisons can be used for individual monitoring services to show compliance with approval accreditation requirements, and of course also to see any peculiar things in their results which they can use for continuous improvement. So the rhythm, try to make clear in this picture, we have the whole body photon intercomparisons every 2 years. These are the blue boxes. And you can see we were able to maintain this rhythm since 2008. Last one was in 2020. So we have together completed 7 versions now, and the next planned for next year. And in between, in the gaps, we try to organize additional special intercomparisons for Extremity, and last time also in addition islands dosimetry. So this fits into the gaps, but we don't do it every 2 years. We do these every 4 years. And finally, in addition, there's also the neutron intercomparisons, which will be talked about by Elena Fantuzzi in the last presentation. And these have a rhythm of once every 5 years. So how did we learn as an organization? Now, obviously, we have many and regular meetings with the organization group, and also with the Working Group 2. But also during the intercomparison, we have a special step. After all the results are there in the draft version, we ask for results, for feedback on the results from the participants. So we can see if there's gone anything wrong during the irradiations, for example. And then after the intercomparison has been completed, we have had always a participant meeting, and in a few cases also questionnaires to ask participants about their experience. Yeah, and then simply by looking how the number of participants develop, we can also learn, of course, a lot about how the intercomparisons are being perceived. And then also we have made a so-called self-evaluation by using the standard SWOT method, looking at strengths, weaknesses, opportunities, and threats. Most of you will be familiar with that. So a little bit detail about number of participants for the whole body photon intercomparison. So I left out now the Extremity and also neutron intercomparisons, just to show you the developments since we started. When we started in 2008, we were already a bit surprised about the large number of participants, but this has been increasing all the time until last version in 2020, which effectively was double number of participants compared to the start. And you can see in the graph, there are always a little bit more systems than dosimetry services in the Intercomparison. That's because some monitoring services participate with more than one system. And the other thing maybe interesting to see is the countries, which is the gray bar, which also increased. Well, we first aimed at Europe especially. Now in the last Intercomparison, there were in total participants from 50 countries, where half of them was from Europe and the other half from outside Europe. So it's really kind of worldwide participation nowadays. Yeah, and to indicate a bit more about the numbers, if you think of each Intercomparison, we ask participants to send in 30 dosimeters. That means from overall, from 2008 until last Intercomparison, we've processed more than 20,000 dosimeters, and of which about 14,000 have been irradiated in well-defined circumstances by ISO 17025 accredited irradiation laboratories. Okay, so some observations from all the things we're looking at. We certainly see that Eurodos certificates for participation of the Intercomparisons are very well accepted by authorities and accreditation bodies. We have received a lot of positive feedback from participating IMSs through the questionnaires and participant meetings. Especially a level of confidentiality and quality is being appreciated. On the other hand, of course, due to the high and still growing number of participants, the coordination and performing all the irradiations are a big and still growing challenge. As continuous concern we look at each time is the concern for having problems with background and transit doses. That, for example, leads to the fact that we are not able to go to too low doses, and we are also looking at ways of changing the organization a bit to reduce the number of transportations in the whole organization. And another lesson we learned was that we take too long for producing the final reports, which can be found on the Eurodos website, by the way. So from all these observations, some conclusions, recommendations, there are many good reasons to continue this cycle of Intercomparisons, obviously. We think of changing the organization a bit in the sense that we would like to appoint a coordinating institute for maybe more than one Intercomparison, preferably not being an individual monitoring service themselves to avoid possible conflict of interest, and possibly to combine this with making the irradiations to simplify the organization and reduce risk of transit dose. Still, we think the organization group should stay as a kind of steering committee, preferably not too big, not too small, 4 to 5 persons, and it should contain a mix of people from individual monitoring services and also people knowing about irradiation calibration procedures and facilities. And we have been working on making the Eurodos reports, the final reports, a bit shorter to produce them faster. So that's about what I wanted to present about lessons learned for the organization. Let me end by thanking especially my colleagues from the organization group for the great work we've made. And let's give the floor back to Marianne.
Thanks a lot, Tom. So let's continue with the lesson learned for photon and betas intercomparison exercises. But again, to know more about the audience, we'd like to launch another poll. So we'd like to know which type of dosimeter do you provide, if it's whole body photon, whole body and sorry, wall body and extremity or islands, wall body neutron, wall body photon and neutron, a combination of above excluding neutron, or a combination of above including neutron. The last answer is if you are not from an individual monitoring service. So now we can continue with Ernest. So Ernest Stadman is a senior engineer in radiation protection and member of the organization group of photon and betas intercomparison exercises. He has coordinated 3 exercises in the past. So Ernest, I leave you the floor. You're muted, Ernest.
Now it should work. Sorry for that. Hello to everybody listening to this webinar. I will concentrate now on the lessons learned for photon intercomparisons from the general results. I will start with the picture of whole body dosimeters, and on this picture, which was from the Intercomparison 2016, you see there are many different types of whole body dosimeters with many different detectors like GLD, OSL, glass, this film dosimeters, and in combination with many different batches, this causes many different and unique dosimetric characteristics for each of these dosimeters. And these characteristics we want to test during our intercomparisons. Probably most of you know this picture. It shows the response values for the intercomparisons, in this case 2018, with respect to dose. And each data point here represents one response value of one dosimeter. In addition, you also see the trumpet curve. You also see the trumpet curve here and here. And when we take a look at the range between the trumpet curve, it seems that the data point, that the response points are distributed somehow equally. This is also caused by the fact that many points are overlapping. If we now make a frequency analysis of all data points, of all 2000 data points, we find out that the frequency distribution of these data points is not at all equal, but it has a very distinct shape. You can see this on the next picture too. You see here the frequency distribution for HP10 for all irradiated dose values. And you see, and this was very surprising for me and very exciting for me, for starting already with the Intercomparisons 2008, that the maximum is very near to 1, and the median value, it's this one here, is also very near 1. That means that for all intercomparisons, the traceability from a primary or a secondary standard laboratory to the individual monitoring service works without big bias. Of course, you can see systems which show a strong under-response or a high over-response, but the overall results, and I will concentrate on these general results, are very fine. If we take a look at different energies, you see here different radiation energies for the Intercomparisons 2018. And if we take a look at the general result, you see that the median value, which is the diamond, is very near to 1 for all irradiated radiation qualities. However, if you take a closer look, you see that at low energies, there is a slight over-response for many systems, and for high energy gammas, there are slight under-response. And this behavior we can see for HP10, but we can see a very similar behavior also for HP 0.07. And this is somehow surprising because the conversion factors for HP10 and HP 0.07 are very different at low energies. So Nevertheless, you find for the dosimeters very similar energy response for HP10 and HP0.07 in a general way. If we take a look now for the angular response, that means the difference in the response when you irradiate the dosimeter from the reference direction and from a wide angle, in this case 60 degrees. So we see these two distributions, and you see that the distribution is somehow parallel but is shifted to an over response. And we can realize that for N60, for a low photon spectra, there is an over response for 60 degree angular irradiation. And if we now calculate the ratio of the response values from 60 degrees and 0 degree, we really can get the distribution of the angular response. And this is the typical distribution for an angular response. And you see most systems, more than 75 systems, show over response for this 60 degree wide angle radiation. And this is for HP10. And in contrast to that, for HP0.07, we see an under response for wide angle radiations for this low energy radiation. If we take a look at linearity, what did we do? We irradiated dosimeters with one radiation quality for low, medium, and high doses, from sub-millisievert to several hundreds of millisievert, and we get very similar distributions for these different dose values. And now again, if we calculate the ratio, of the response values, for instance here, calculate the ratio between the response for high dose and for low dose, we again find a distribution for the linearity. And here we can see that the linearity is very close to unity, and the median value, for instance, is here an over response for for low dose values for with 4% only. So in principle, linearity for all systems is quite well, and there are no big outliers for that. And now something about reproducibility. We always irradiated pairs or 4 pieces of dosimeters with the same dose value, and then calculated the coefficient of variation for these 2 or for these 4 equally irradiated dosimeters. And when we do that, we get a frequency distribution of this coefficient of variation. And you see here that 50% of all dosimeters, which is the median value, show those values, show a coefficient of variation smaller than 3.4%. And this is something that surprised me very much, that so many systems show a very, very good reproducibility for equally doses for the same radiation quality. So we, of course, find also systems with very high coefficient of variation, but the majority of systems showed a very good reproducibility for this setting. And now I want to talk a little bit about outliers concerning outliers with respect to ISO 14146. And here are different intercomparisons, 2018, 2016, 2014. And what you can see here is that the number of outliers has the maximum always at low energies and high angles. This is something that we observed. And we also found out that the overall fraction of outliers of all data points is more or less between 5 and 7%. And it, of course, strongly depends on the selection of the different radiation qualities that the OG defines before each intercomparison. Now we go to extremity dosimeters. Here I show some pictures of the Extremity Intercomparison 2019. In the rear, you see many different ring dosimeters, and in the front picture you see fingertip dosimeters, and here there are wrist dosimeters, which are used in some countries. So you see, when we consider extremity dosimeters, there are different kinds of dosimeters which are also needs to be individually took into account when we make an analysis. All these systems show dose values in HB 0.07, but needs to be irradiated on different calibration phantoms, and different conversion factors needs to be applied. Here you see the angular and energy response, and here you can see that we carried out beta radiations and also X-ray radiations and gamma radiations. And the energy response for X-ray and gamma is quite smooth. You see very close values of the median value to 1, although we see a very similar behavior like we have seen already for whole body dosimeters, that for low energy photons there is slight over response. But what you can see here also is that for beta radiations there is a very strong under response for the krypton radiation quality, which has a very low beta energy. For strontium and strontium with angle of 45 degrees, it's somehow okay, the results, but the krypton results are very, very low, and only very few systems show successful results for these krypton irradiation response values. If we take a look at the outliers for this intercomparison, we see here for photon dosimeters, for photon and beta dosimeters, and combination of all, we see again that the outlier rate is extreme for the krypton 85 radiation quality, and the overall outlier fraction is also about 6% for the extremities. If we go now to eye-lens dosimeters, which were irradiated at the same intercomparisons 2019, you see here a selection of only some eye-lens dosimeters. And if we take a look again at the energy and angular response, we see again good results for X-ray and gamma irradiation, for photon radiation, and for beta radiation we irradiated with strontium 90. We see the median value is quite okay, but there is a very widespread. Some systems show under response, but many systems show over response, and this might be the fact that the filter or the housing of the dosimeter is just too thin. That means that beta radiation can enter the sensitive volume and thus increases the response of these dosimeters. Again, a picture of the outliers for the eye-lens dosimeters. Again, many outliers for strontium 90. And the overall outlier fraction is something about 10% for this intercomparison. Now, lessons learned for whole body dosimeters. We have many different dosimeters. The mean response is very close to unity, but we find a slight over or under response for low and high energy photons. The angular response for low energy photons for HB10 and HB 0.07 is different. Most systems show a very good linearity, and the reproducibility is also very fine for the majority of all tested systems. If we take a look at the extremity and eye-lens dosimeters, we found one significant problem with all these dosimeters, or with many of these dosimeters, that we see significant problem for low energy betas for HB 0.07 and betas in general for HB3. I thank you very much for listening. This was my presentation, and now Anna will talk about special cases. Thank you very much.
Thanks a lot, Hannes, for this general overview, very clear. So before switching to the individual result, let's launch another poll, the last one. We just want to know if you have already attended Euredos Intercomparison participants meeting that is usually held at the annual meeting or linked to a conference. So please, you can answer to this question, and then I will leave the floor to Ana Maria Romero, which is the head of the CIEMAT dosimetry service in Spain and member of the organization group of the intercomparison exercises for photon and betas. So,
thank you, Marianne, and good evening to everybody. I'm going to present the information that participants can learn from the results and some particular behavior of whole body, extremity, and islands dosimeters that we have found during this intercomparison. So the radiation plan. The radiation plan is designed to check some of the performance of some important characteristics of the dosimetry systems. So, for example, linearity. In all intercomparisons, we have irradiated those meters to 2 or 3 dose values, low, medium, and high doses, for the same radiation quality, so we can check the linearity of the system. Also, angular response, because always we irradiate those meters in normal and angular incidence to a similar dose, but and with the same radiation quality to check the angular response. Also, the energy response, because we use usually a wide range of energies overall for gamma, so from low energy X-ray to gamma radiation. And also we have checked the response of to mixed fields, irradiating the dosimeters to 2 different radiation fields. Also, for always for extremity dosimeters, we check or we irradiate those meters for the IMSs to check the response to beta radiations. And here, for example, for extremity, we usually irradiate those meters to 2 different beta radiation qualities. And for whole body dosimeters in 2016, we checked the mixed fields, the whole body dosimeters for mixed fields, photon and beta radiation. But also it's very important for the participants to check or to test their compliance with ISO 14146 with the so-called trumpet curves that really indicate the performance limit of the system. So let me show you now some examples of whole body dosimeter performance. We have, as Hannes mentioned, we have different type of dosimeters, and for the analysis we have divided in film dosimeters, TLD, OSL and other type of dosimeters as radiophotoluminescence dosimeter, direct ion storage, or active personal dosimeters. So for field dosimeters, for example, we have found a very wide range of performance with systems that performs really well and systems that have problems. The same behavior is found for TLD dosimeters. We have very, very good systems, but also systems that present many, many problems. However, for OSL and for other types, the number of outliers has been always less. They show in general good, very good performance. If we check the linearity, we found that usually the problems with linearity comes from the evaluation of high doses. We have systems that perform that present a sublinear response or a supralinear response. So for this kind of systems, they are really good response, but only that problem. Maybe it could problems with the reader. There are some readers that have two counters, one for one for low doses, one for high doses, and both should be calibrated, and maybe they have this kind of problem, or problem with saturation, for example, in films, dosimeters, or with some kind of detector materials. For the angular response, in Intercomparison 2016 and 2018, we checked two different angular response to the angular response with two different radiation qualities. So one for beta and one for X-ray. So we can, in general, we got that most of the system perform better for photon radiation than for beta. The angular response was better for photon than for beta, but also found some systems that the beta angular response was really poor. So maybe it can be a problem of range of application of the dosimeter. Maybe that dosimeter is not intended for that kind of radiation. If we have a look of the energy response, we found different behaviors. We can find dosimeters that performs relatively good or good for X-ray, but they have problems with gamma, or we can find the opposite behavior. So that can be due to the intrinsic characteristic of the detector material, for example, that show our response to low energy photons or X-ray. It also can be a problem of the algorithm or the batch design, or even also the range of application of the dosimeters. There are some dosimeters that are mostly applied in the field of radiodiagnostic, and so then they are calibrated with radiation qualities applied for radiodiagnostic, and they don't have a good response for gamma, for example. But also, we have found systems with a very, very good energy response, but many outliers. And that is a problem very often in many participants, and it's a problem that can be solved improving calibration procedure, improving by checking calibration factor. So for the mixed radiations, we have found behaviors that are, for example, for response is
It seems we have lost the connection with Anna Maria. So maybe while she's trying to connect again. Oh, well, she's trying to connect.
And gamma fields, we found systems that, for example, show it. Just one moment. Sorry. This one. That show it remarkable over response for mixed beta and gamma field, even when they show it a good response for beta and for gamma. And however, for the estimation of HP 0.07, that is not the case. So maybe they have problems with the algorithm or the batch design. So one of the conclusions for whole body dosimeters is that there is a wide range of performance. There is a way. Sorry. Okay, I can see it on my screen, but okay. There is a wide variation of performance, but all kinds of systems can work well if you use the correct procedures. And for example, we have seen that OSL and other systems present fewer outliers than the others, and that high doses come from linearity problems come from the high doses, and improvement is always possible by checking calibration procedure, algorithm, and batch design. And we have also seen that HP 0.07 response follows the same trend that HP 10, but usually with a lower performance. If we have a look to the extremity dosimeters, are very similar results. I think I'm short of time, so I will go a little bit faster. We can find good and poor performance also in extremity dosimeters. And even, for example, we have for photon only, we have dosimeters intended for measuring only photon or for both photon and beta radiation. And some of the only photon dosimeter also showed an acceptable response to beta strontium radiation. And for beta plus photon dosimeter, we also found good performance and very poor performance for both, for gamma and for photon and for beta. So having a look at the, I'm sorry, but it's that I can see my presentation here on the screen, so sorry for that. So we also found that linearity problems come from high doses, and we found sublinear or supralinear response in both types of ring and wrist dosimeters, and the reasons can be the same for the whole body dosimeters. And for the angular response, we have examples of very good performance for rings, for wrist, and for fingertip dosimeters. But also, we have found that the angular response is remarkable worse for beta radiation than for photon. So this is caused because the higher influence of the filtration in the design of those meters for beta radiation. And in general, Hannes has already mentioned that we have found that extremity dosimeters have problems with the low energy beta radiation with krypton. Always underestimate. And for mixed strontium and cesium radiation, we have found systems where the behavior is very coherent, but we found one system that we don't have any explanation, where beta and photon response is very good, but for mixed radiation, it works very badly. And the same calibration problem can improving calibration always can diminish the number of outliers. So conclusions are very similar, but one of different is that the photon beta dosimeter showed better performance for photon than for beta radiation. And for islands, we have photon and photon plus beta dosimeters. We also have, as usual, good results and bad performance for photon only and for photon only and for beta, photon and beta. For linearity, we have found systems with a high underestimate of the high doses and others with excellent linearity. Always calibration can improve the results of the participants, and we haven't found particular problems in angular response for islands dosimeters. So for beta, we have a similar trend than for extremity dosimeters, but many systems show it an over response to strontium that was not shown in the extremity dosimeters. So conclusions are very similar. Always check calibration, calibration procedure, calibration factor, and this in particular, a particular conclusion is that all dosimeters showed a very good angular response. So thank you for your attention, and I pass the floor to Marianne to present Elena.
Okay, thanks a lot, Anna Maria. So we are quite running out of time, so we have to change our mind and our plan. So we will directly answer within the Q&A chat or in the public chat, and we fear we will have no time for a specific time question session. So look in the Q&A session to have the answer. So Elena, I leave you the floor. To finish with the specifics of the neutron intercomparison, you're the head of the Radiation Protection Institute of Linearity in Italy. So I leave you the floor.
Thank you, Marianne. Thank you. Good afternoon to everybody. My talk is about neutron intercomparisons. It will be more general compared to the ones you have just heard on photons. And my talk is given also on behalf of the other members of the organization group of the EuroDOS intercomparison. 2 intercomparisons on neutrons took place already, one in 2012 and one in 2017, and the next one is expected for next year. The organization group was quite similar for both editions, and the participants meeting took place either at the conference EuroDOS 12 for the 2012 comparison or at the annual meeting, EuroDOS annual meeting in 2019. For the first intercomparison, the EuroDOS report with all detailed information is already published. For the second one, the report is expected within this year. And just a few words about the aim of the intercomparison for neutrons. Actually, the aim is to perform to test the performance of neutron dosimeters, which are actually used in routine to monitor exposed workers. So no systems under development are allowed and will not be allowed, because these are out of our aim. The main differences from EuroDOS intercomparison for photons, there are quite many. Main ones, as already mentioned, the neutron intercomparison frequency is only every 5 years, mainly due to the costs of the radiation labs, but also because of the number of participants is less. In fact, we had 30 participants, and as IMS is active in neutron dosimetry, are quite fewer than for photons. And also for the fact that the availability of the reference radiation fields is not the same as for photons, and the neutron dosimetry is somehow more challenging than for photons. We had the two intercomparison. One was as a 2-step procedure and one is 1-step procedure. I will speak about this later on, and also the evaluation criteria is different for neutrons and photons. Just few words about the neutron fields. Actually, is the workplace fields. On the left, you can find the measurement values of workplace fields measured during the EVIDOS project. So the workplace fields cover more than 10 orders of magnitude. And not only is the calibration or reference field have the same characteristics, and it's quite difficult to simulate with reference fields the workplace fields. On the right, you have the examples of the neutron irradiation fields that we use for the 2017 intercomparisons. As you can see, the fluence and the HP10 curve for the calibration radiation fields that we used. The features of the intercomparisons of the two intercomparisons are quite similar for the number of participants. the number of dosimeters used. We kept some of the radiation fields similar for the two intercomparisons in order to compare the results of both. And then, as I mentioned, the first one was a two-step procedure and the second one step. For the first one, there was not a internationally agreed criterion to judge the performance of the intercomparisons. So the organization group decided to use a factor of 2 criterion based on the statement, ICRP statement, which allows the accuracy, the uncertainty for Newton dosimeters can be within a factor of 2 instead of a factor of 1.5 as for photons. For IC 2017, we managed to have the evaluation criteria agreed, internationally agreed, because following our recommendations, the ISO standard 14146 was revised and reviewed and was published. So here you can find the limits used to analyze the results. The blue lines are the factor 2, which we use for 2012, and the green lines are the 14146 ISO standards limits, which allows wider range of the response for lower values, lower response values. I mentioned one-step procedure as during the first intercomparison we realized that some of the albedo dosimeter-based system need to have somehow a priori information in order to apply the proper calibration factor for their routine system. We realized that we cannot make a real blind test, but we had to provide some information on the radiation fields. So for the second run, we decided to ask at the beginning to the participants whether they need or not the a priori information. And 22 out of 33 participants declared they need, but almost all the albedo services and half of the track services providing track dosimeters. So the ones who didn't request information just had the information that the dosimeters were irradiated, and the other ones got simplified a priori information. And these are the dosimeters for 2012, this for 2017. All the dosimeters have been grouped into 3 main groups, but for the first intercomparison, but actually in 2 main groups, which are the albedo dosimeters and the track dosimeters. But we have to say that within these 2 groups, you can find dosimeters which are very differently assembled. For example, for track dosimeters, you can have track dosimeters just for fast neutrons, and some others with TLD or sensors for thermal neutrons or thermal neutron converters in front of the track detector. Whilst for the albedo, you can have TLD with cadmium shield or boron-loaded shield or OSLD or any. We don't have any information on how they shield the incident neutrons, thermal neutrons. Here is our overall results, general results for the 2012. I didn't put the legenda of these symbols, but I will put it in the presentation you will find on the Eurodos website. So the box, let's say the blue dot is the mean value. The box represents the 50% range of the responses. The red vertical line, the 90% range of the results, and the triangle up and low are the maximum and minimum value for the irradiation categories you found on the x-axis. So as a general first look, you can find that the mean of the all results is quite equal to 1. Nevertheless, there is quite a wide spread of the responses. In this other figure, you can have the same results, but here is the two types of dosimeters is shown, and so the responses cannot from the responses you cannot really derive a trend of better performance of one type over the other of dosimeter. Again, you can find that all the results most of all are within the factor, the limit, the factor to limit dotted lines. Nevertheless, there are some of them quite far away. The spread of here the 250 keV monomagnetic field was quite challenging for a lot of systems, and the same graphs for IC 2017. Here you can, the meaning for the symbols is the same. So the boxes which represent the 50% of the response is quite narrow, more narrow than for the previous intercomparison. So the results seems improved. They have improved. Nevertheless, there are some radiation fields which show some challenges for most of the services, like the D2O californium source behind a shadow block, which is a simulated workplace field, which with a quite high percentage of thermal or anyway moderated neutrons. Here again, the same results with the differences between track and albedo. The dot lines, horizontal lines, are the limits for the ISO 14146, which is different from each those values. And again, you cannot really spot any trend of, between the two dosimeters, the type of dosimeters. One general comment: these are just for IC 2017. The graphs for the irradiation are bare californium at 0 degrees, which is somehow the calibration conditions, and so it is clear that there's still a spread of results, and still some values outside the limits, even though these conditions should be at least quite simple. And the last one on the right, on the bottom on the right, it was a radiation field with californium with gammas, which shows that even track dosimeters had problems with additional photons. As an overall comment, we can say that in IC 2012 we had less than half of the participants who had only less than 2 outliers within the limits. In 2017, the results seem to be better, because 21 out of 33 had less than 2 outliers within the ISO limits. But some of them, for almost half of the participants, showed very good results, with all the results within the limits. Here are some comments related to each radiation fields, but as we are running out of time, I go to the main lessons learned. And as organizer for the intercomparison on neutrons, we can say that the first lesson that we realized that we cannot really perform a blind test for neutrons, because some of the system need a priori information, and we had to reduce as little as possible the information that we still need to provide to the participants. Another lesson was that there was not the criteria performance for the performance limits for neutrons, but this gap was filled with the ISO 14146 published in 2018, following our recommendations. And the other is that in the one-step procedure, almost more than half declare that they need a priori information, while we are quite sure that most of them actually act without any a priori information. So we should find a way not to allow information different from their routine procedure. As IMS dosimetry community, we can consider that low doses like 0.3 millisievert are still challenging for some participants. 250 kV is still challenging as intermediate neutron energy for many truck systems currently used. And general better results for radionuclide bare sources compared to simulated workplace fields. And strange results for neutron and gamma discrimination, which will be investigated further. As a conclusion, we can say that both exercises showed that the need for development in neutron personal dosimeters. The results are generally good, though some participants can show quite poor results. The results of the intercomparison are very important not only for the IMSs, but also for authorities and accreditations. We cannot conclude there is the best type of dosimeters because we could not find any trend of better response for albedo track dosimeters. And it is clear that the management of the system and influence the results, because you can have quite different results with very similar dosimeters. All the details on the neutron intercomparisons are published in this publication, which are available on the Eurados website and in the report, Eurados report. So this is everything from my side.
Thanks a lot, Elena. So we are quite running out of time. So all the answers that you have written in the public chat or in the Q&A chat was answered. If you have more questions, you can send an email to myself and then I will transfer to my colleagues to have an answer. And just for you to share the information and the result of the different polls, you were about 64% people from individual modeling services that have already participated to Eurados intercomparison, 9% from individual monitoring service never participated, and more or less 10 or 20% in the others work area, calibration service, commercial company, etc. For the type of dosimeters that you provide, I have about 45% of a combination of above, meaning a wall body plus extremity or lens photon dosimeters, and including neutrons. And the last is if you have already attending Eurados intercomparison participant meetings. It seems that not so many because 70% answered no. So we need to enlarge this participant meeting maybe to share all this information. To conclude, I'd like to thanks a lot all the presenters that gave us a very nice overview of all these intercomparison exercises done within this all these past years. And thanks for the participants for attending this webinar. The next one will be on 25th of November about correlating micro and nanodosimetry with initial biological damage. So thanks again. And maybe the answer.